We started in chapter 6 on Tuesday before break. Let me start with the notion of a power set. So let's let A be a set. I'm not going to say much more about the set A. It could be infinite, it could be finite, it could be empty for all I care. The power set, which is denoted P of A, try and use like a curly P or a bold P or something like that, is the set of subsets of A. So this is going to be all B such that B is a subset of A. So it probably be worthwhile to write down exactly what's meant by subset, although we probably used the notation before already. So if A and B are sets, then what is meant by these symbols, A is a subset of B, well, I probably should write it in words, then we say A is a subset of B, denoted this way, if all of the elements of A are also elements of B. So I'm going to be very symbolic about this. I'm going to say, given any X, saying that X is an element of A implies that X is an element of B. Okay, so this is a definition. This is a definition. I want to talk through this a little bit, and then I want to just explore some examples so we get familiar with the notion of power set and notion of subset. First off, this definition right here suggests a sort of proof technique if for whatever reason you had two sets of interest and you wanted to prove that A was a subset of B. So since it's a for all statement and a conditional here, you could go for like a direct proof of the conditional. You could say let X be arbitrary, suppose X is an element of A, and whatever that gets you, use it to prove that X is an element of B. Such an argument is called a point chase argument or an element argument. I'll say more about that when we're actually working with a specific proof. Given any particular set A, there may be, many subsets. If you gather them all together and put them into set braces, forming a set out of them, then that is called the power set of the set A. All right, so let's inspect some examples just to familiarize ourselves with the concept. Okay, everybody's favorite set is the empty set, right? So the empty set is a set. It's a perfectly good set, but it doesn't have any elements in it, right? Okay, the power set of the empty set, is the set, okay, of all subsets of the empty set. So I got to think about that for a second. So question, does empty set have any subsets? Okay, and answering this question will give us actually sort of a more general result. So pause the video and try and answer that question. All right. Let me prove to you that the empty set does have a subset. Well, exactly one subset. The empty set is a subset of itself. Okay, and let's sort of argue why this is true. And we can use a so-called point chase argument to do so. Let X be arbitrary. Look, the statement X is an element of the empty set, that would be like this part of the conditional, that statement is false for all X, right? That's what it means for the empty set to be empty. So this statement is false, hence the conditional statement is true, right? Sometimes we say Empty set is, empty set is a subset of the empty set. It's vacuously true because of this strange thing that our conditionals are true when their premises are false. Okay, so it has exactly one subset, that is the empty set. So look at the difference between the nature of the empty set and the power set of the empty set. They don't look the same, right? I've underlined the empty set here, and I've underlined the power set of the empty set here. They are not the same set. Pause the video and think about what makes them different. If you said that the difference between this set and that set is that this set has one element and this set has 0 elements, then you're right. That is the difference between these two things. Now this leads us to a general observation. So given any set, let's say A, it has, well, actually I can say two things. It has at least two subsets. A is a subset of A, and empty set is a subset of A. If you wanted to prove that empty set was a subset of A, you're looking at least the same front part of this conditional down here. So that statement is going to be vacuously true for A replaced here. But also, any element of A is an element of A. You're just repeating yourself. So this sentence is also true. It's only in the case that A is the empty set that these statements say the same thing. But in general, that's two separate things you can say about a set A. Now, I want to rewrite these statements carefully using like the power set symbol. And this can get a little tricky, but part of the point of this chapter is to get you familiar with this language. So I'm going to use the fact that the power set is the set of subsets. So its elements are subsets of A to rewrite these two statements. So the first statement says A is a subset of A. That is the exact same thing as saying A is an element of the power set of A, because the elements of the power set of A are exactly the subsets. So this is another way to phrase that, and likewise, this is also a true statement. Okay? So, oops, I meant to say IE. So given any set, A is a subset of A, and empty set's a subset of A. And those are rephrased in terms of the power set. So get used to this sort of notation here. Be careful. This right here is not generally true, okay? I mean, actually, if you're studying set theory properly, you actually forbid this from ever happening. So a set is not an element of itself, generally. So for example, I'm gonna just use some of our number sets to write down some true statements and some false statements, again, to just get a feel for these concepts. So like a lot of things are true, like the rational numbers as a set, that's a subset of the real numbers, right? That makes the rational numbers an element of the power set of the real numbers, right? Screwed up that P. So those are both true statements that I have written, right? Let me put green T's next to them. But if I say something like this, Q is an element of Q, that's no good. That's not a true statement. The elements of Q are numbers. They're not other sets, all right? And likewise, saying that Q is an element of R, that's also just not true because, again, the elements of R are numbers, and the Q itself is a set of numbers. So this set of numbers can't be an element of R just because of how R is constructed. So don't conflate these two expressions. Q is a subset of R versus Q is an element of R. That's not to say that sets can't have other sets as elements, right? Like if I let the set A be 1, 2, the set that has 3 and 4 in it, and I let B be the set 3, 4, then this is a set of numbers. This is a set that has some numbers and a set in it. Saying that B is an element of A is actually true, okay? Because I do see B as an element of A. Okay, so here's a couple questions sort of in both columns here. Let's see here. Is B an element of the power set of A? Question. And then let's say something like this. Is Q an element of the power set of Q? Just pause the video and see if you can get an answer to those two. Here, the answer to this question is, this is going to be no. This is no, because B is not a subset of A. In order to be an element of the power set, you would have to be a subset. So look, in order for B to be a subset of A, all of the elements of B would have to be elements of A, and they're not. So if I want to demonstrate that what I've just written here as a claim is actually true, I can demonstrate. 3 is an element of B, and yet 3 is not an element of A. And so again, if I glance up here and see what it takes for one set to be an element of another set, I need for all of the elements of the first to be elements of the second. So in this way, B is not a subset of A. And notice that my little argument here, my little proof that subset didn't happen, since subset is a for all statement, my argument, my demonstration was that there exists. I prove there exists an element that is in B and not in A. So anyway, disproving a for all statement is that there exists. Okay, the answer to this question, I hope you decided, was yes. This is true because Q is a subset of Q, right? And this is just, based on the more general argument that we had a little bit ago, that every set is a subset of itself. So I want to make an observation about power sets, at least finite power sets. So suppose, this will be a fact that I'm writing here. Suppose that A is a finite set. We'll talk about cardinalities of infinite sets later, but for right now, I just want to make an observation about the cardinality of the power set of a finite set. So suppose A is a finite set. Say A has n elements. This is how we represent that. Then the number of elements in the power set is the number of subsets of the set A. So pause the video and take a guess for what that number is. Okay, I'm going to sort of write down the answer and explain it all at once. Maybe an example will help do that. So let's say I have a finite set. Let's say it has cardinality 3, right? If I'm to list out all the subsets, I already know that empty set is going to be one of them because empty set's a subset of any set. A is going to be another one, right? So the full set 1, 3, 5 is a subset of itself. Well, then we're going to have all of the singleton sets, those sets that only have one element from A in them. And then we're going to have the two element subsets. So I think I magically left enough space for all of these. This is a full set or full list of these subsets of A. Because if you're a subset of A, you either have 0, 1, 2, or 3 elements. And I've exhausted all of this. Note that going into constructing a sort of random subset of A, I have a sequence of 3 choices to make. I can put the element 1 in there or not. I can put the element 3 in there or not. And I can put the element 5 in there or not. If I say no to each of those choices, then I'll construct the empty set, right? If I say yes to all those choices, then I'm constructing the set A, right? And then I can do like any combination of no's and yeses. I could say no to 1, I could say yes to 3, and then I could say no to 5, and that's going to create the set 3, subset 3. So I get the idea that sequences of no's and yeses are in one-to-one correspondence with the subsets of A. So in this way, like I have for A, manually 1, 2, 3, 4, 5, 6, 7, 8 elements of the power set, and A has cardinality 3. So let me just kind of clean all this up. This is the power set that I've listed here, right? It has 8 elements. And in general, like if you have n elements in A, then you're looking at the number of sequences of yeses and nos you could make. That's going to be 2 to the power n. So this is a general fact for finite sets. If you know the cardinality of the finite set, then you know the cardinality of the power set. And let me just say that this works in the trivial situation. The cardinality of the empty set is 0, it doesn't have any elements, but as we observed before, the cardinality of the power set is 1, okay? It follows this formula is all I'm saying. Okay, and I mean, there's something related you can say about infinite sets, namely that the power set of an infinite set is strictly larger than the cardinality of the original set, which seems kind of weird because you'd need more than one level of infinity, but there actually is such thing in set theory. All right, let me move on to some other topics that I want to talk about in this section. So I want to talk about Cartesian products right now. In order to do that, I need to introduce the notion of a n-tuple. So let A1, A2, up through, let's say, AN, just be a list of sets. So let all of these be sets. Again, I don't care about the particulars. These could be finite sets. Some or all of them could be empty, whatever. Let those be sets. All right, so let me say what an n-tuple of elements from these sets looks like. So if A1 is some element in the set A1, and little a2 is some element in the set A2, and so on, all the way up to AN. Then when you list those elements using parentheses like this, so it's just a formal list. So A1, comma, A2, comma, A3, all the way up to AN. So it's like a sequence, right? But it's finite. Then that list in the parentheses is referred to as an n-tuple. Is called an n-tuple. Okay, and just like for some conventions, like if we're talking about n equals 2, and we write something like this, A1, A2, that's called an ordered pair, right? Ordered pair. We don't really call it a 2-tuple because that's obnoxious. We call it ordered pair. And then if we're talking about n equals 3, so we've got 3 sets and we're sort of listing 3 elements, each one taken from one of the sets, A1, A2, A3. That's called an ordered triple. Okay, and you could have like a ordered quadruple and so on. But usually, like, by the time you get to 4 or above, you just say 4 tuple, 5 tuple, 6 tuple, whatever. So in certain instances, you're interested in, you know, several sets all at once, and you want to consider, you know, sort of ordered n tuples from those sets. N tuple. Okay, let me, I gotta introduce the Cartesian product then. So if you gather all of the possible n tuples from a sequence of n sets, and you put them into a set in its own right, then you've defined what's called the Cartesian product. So the Cartesian product of the sets A1 through AN is the following set. First, I'll show you the notation. It's a product in some sense, so we use little time signs to represent it. It's sort of a notion of multiplication for sets. Be careful, these are not numbers or something. This is just a symbol we're borrowing from arithmetic to express something. So what this is the Cartesian product of A1 to AN. It is the set of n tuples, like this, where, as I said before, A1 comes from A1, little A2 comes from A2, and so on. So if you gather together all of the n tuples from these n sets and put them into a set, then this is called the Cartesian product of those sets. All right, and I mean, the most familiar context for Cartesian products is like calculus or even geometry or something. So let's consider the situation where both of the sets, I'm going to consider two sets, and I'm going to make both of them the real number set. So when I talk about R cross R, that's sometimes how it's read, cross. I should put those in words here. You read that cross. So what is this? This is the set of ordered pairs of real numbers. All right, or two tuples of real numbers. And like we visualize R cross R as a plane because it's just a convenient way to chart all of the ordered pairs. So the convention is to chart the first coordinate of the ordered pair along the horizontal axis and the second along the vertical axis. So calling this point A comma B is saying that this is A on the number line and then this is B on the number line. So you guys know how this is called the Cartesian plane, of course. That's how it works. Of course, you can do this in any dimension. So if you take like R cross R cross R, that is the collection of three tuples of real numbers. And you can kind of get a drawing of three-dimensional space. This would be called three-dimensional Euclidean space. And you just need three axes, and usually you only draw the positive axes because it gets sort of hard to keep track of the negative axes. So saying a point in 3 space is A, B, C, depending on your convention, but in mathematics usually this is the first coordinate, this is the second coordinate, and this is the third coordinate. So saying that this is the point ABC is saying you're sort of like A out on the x-axis, B out on the y-axis, and then C up on the z-axis. That's what we're saying. So you plot points in 3D. All right, I'm going to just make a really, really subtle note here about notation. The book kind of asks you to explore this notational subtlety, so I thought I would give you a heads up. There's a difference between sort of formally this expression right here versus this expression. So we just explored the collection of ordered triples of real numbers, right? It's just formally all the different lists of 3 numbers that you can make, right? You toss them in a bag and you visualize it like this, right? This technically is the Cartesian product of 2 sets, the second of which is just the real number set, and the first of which is the set of ordered pairs of real numbers. So let me write out formally what this is. First, I'm just going to write out the factors. So like this right here is, as I've got written up there, all of the ordered pairs of real numbers. Okay, and then this, the second term, is just the real numbers, right? Well, if you're going to expand this, if you're going to write down what's actually here, this is going to be a collection of ordered pairs, or 2 tuples, one of which is taken from here and one of which is taken from here. So like if I'm going to do that, I'm going to make 2 tuples like this. Then I have to take n elements of this set and put it in the first slot, and n elements of that set and put it in the second slot. So this is almost stupid, but this is formally what this computes out to be. They're different things, technically. I mean, just the introduction of those parentheses somehow has made the nature of the set different. I mean, mathematicians don't really... I mean, these would both be interpreted exactly the same way because fundamentally they are the same thing. They are the collection of lists of 3 real numbers. But formally, this one has more parentheses in its elements, you know? So it's a subtle and kind of stupid distinction, but just be aware that the symbols here mean something. They actually do produce different objects. You got to think about that for a second. Make sure you understand what I'm saying here. Like, why is this equal to that and this one's equal to that? You got to think about it. That also reminds me that there is often an abuse of notation, so I want to just warn you right off the bat. This right here, that's not how you express R cross R. You don't put sets typically in the coordinates of a tuple, all right? If you're trying to talk about ordered pairs of real numbers, you write this right here. This is good. Don't ever write that for that, all right? What else? Sort of conversely, don't write this either. If these are 2 real numbers, don't write A cross B to mean this, okay? I mean, A times B already means, like, numerically A times B. So don't conflate the parentheses and comma notation with the cross notation. The cross means collection of ordered pairs or n tuples more generally, and then this is how you actually express those individual n tuples. All right, let me move on to the last topic that I want to talk about in this lecture, and that is partitions. So suppose A, curly A, is a collection of sets. Now this is we're getting a little meta here, but I'm going to be considering all at once several, potentially lots of different sets. I mean, kind of like I was up here a second ago. I mean, if you give me n different sets, I can form one set that is their Cartesian product, right? Yesterday or Tuesday before the break, we talked about, unions, like bigger unions of collections of sets. So you could even have like infinitely many sets. So I don't really care about the particulars about this collection of sets. Like it could be a finite collection of sets. Let me sort of write that out. Like A could be the sets A1, A2, up to some AN. So it could be 5 sets or 10 sets or whatever. or it could be infinite. I don't really care. And, you know, in another class, I would even be more general about this. This is a certain level of infinity that I just marked off here. But, you know, in general, curly A could be a really, really largely infinite collection of sets, whatever that means. But for our purposes, just think of A as like either a finite collection of sets or an infinite collection of sets that are indexed by the natural numbers or something. Okay, so start with that, and imagine that each one of those sets was a subset of some other common set. So actually, I might even modify how I started this sentence to support that. So suppose that A is a collection of subsets of some common set A. Oops. Okay, so we're talking about like Venn diagram here, right? Like you got some set A that you're interested in, and you're grabbing a bunch of subsets potentially. So this might be A1, this might be A2. Just grab a bunch of sets. All right, so I've got this definition which pops up in a ton of places in mathematics. The notion of a partition. So we say that A is a partition of A if a number of things holds. So first off, the sets in the collection A have to all be non-empty. We don't allow empty sets to be part of partitions. It sort of screws things up. So A has only non-empty subsets of A as elements. Okay, secondly, the members of curly A in some sense cover all of A. Like if you're to draw the Venn diagram, they completely like color in all of A. So one way to say it is the union of the elements of curly A is all of the set A. So let me just spell this out in the two different situations that I could have here. So in other words, A is the union of the AIs. I equals 1 to n in the case that curly A is a finite collection of sets, or like if it's an infinite collection of sets in this way, A would be the union I equals 1 to infinity, all of them. And lastly, this is the one condition about partition that my picture doesn't match at all. The collection is pairwise disjoint. That's my word for it, and then I'll just rephrase it slightly. So pairwise disjoint. And what I mean by that is for any two indices here, if I is not equal to J, then AI intersected with AJ gives you the empty set. Okay, so all this means is that the different sets that are in curly A don't have any common elements, right? So a better picture of a partition of A would look like something like this. Okay, I'm making them all sort of like perfectly square, but like this might be A1 and this might be A2, this might be A3. You see, they don't hit each other at all. Like the A1 set doesn't intersect the A2 set. They have no elements in common. And as you can see, like when they're taken all together, they fill up A entirely. A very common example of a partition is when A is the integers. You can take something like mod 2 or mod 3 or mod 4. Let's do mod 3. And you can use it to sort of partition the integers up in the following way. Let's say I let set number 1 be all of the integers that are 0 mod 3. So if I took n mod 3, I would get 0. So those are, in other words, what are those numbers going to be? They're going to be all the multiples of 3, right? A2 might be some other integers. It's not going to be the multiples of 3, but those integers that when divided by 3, you get a remainder of 1. So clearly, n can't be both 0 mod 3 and 1 mod 3, so these are definitely disjoint. I can also name several integers that are in both of these sets. Like, what I mean is neither of these sets is empty because there's tons of multiples of 3 and there's tons of numbers that are 1 mod 3. And then the only ones missing, if I want to cover all of z, are those integers that have a remainder of 2 when divided by 3. So in other words, n mod 3 is equal to 2. So if I put these 3 sets into a larger collection called curly A, then they form a partition of the integers. So I'm just going to state that as a fact, and you can kind of think about why that's the case. So this is a partition of the set A, which in this case is Z. So you can check off the requirements to be a partition one by one and see that this is the case. And it's not just 3. You can similarly partition Z up into 7 pieces by using mod 7. And I mean, that's one of the most common partitions you'll see that shows up in math areas like algebra. But as I said before, partitions kind of show up a lot in all kinds of branches of mathematics. All right, let me pose some questions so you can practice with these topics. So, whoops. All right, question number 1. Can you come up with an infinite partition of Z? So what I mean by that is, we've just seen some finite partitions of Z using the mod relation. But is there any way to take the integers and split it into infinitely many pieces, hence creating a collection curly A that has infinitely many sets in it? So pause the video and see if you can do that. Okay, here's one potential answer. What if I define the collection A as follows? What if I group together, well, let's say I put 0 in its own little set, and let me group together -1 with +1 in a set, and then I group together 2 with -2 in a set, and so on. I hope you can see the pattern of what I'm doing here. So, this is one infinite partition of the integers, I claim. So, first off, and actually I can write this sort of shorthand if I like. I can say that this is all of the sets that are of the form -n, n, where n is in Z, and you might say, well, wait a minute, what about 0? The singleton 0 set doesn't look like that. Well, it actually does. -0, 0 is just the set that has 0 in it. Let me sort of argue that this collection has all the properties it needs to have to be a partition, but it's also infinite. Well, I think obviously the collection A is infinite because it's got as many sets as there are natural numbers. And let me just go through 1, 2, and 3. Each of these sets that I've defined is non-empty, right? The first one has one element in it, and all the rest of them have two elements in it. So they're all non-empty, each one of the members of curly A. What's next? Is the union equal to the integers? Yeah, actually it is, because if I think of like, actually let me get another color. If I think of this set as like a 0, and this set as like a 1, a 2, and so on, I hope you can see that the entire set of integers is indeed the union I equals 0 to infinity of AI. Every single integer appears in some a sub I, like 1 million is in a 1 million, and so on. So 2 is satisfied as well. And then lastly, are these sets pairwise disjoint? Yeah, I mean, if you take AI and AJ for I not equal to j, then the intersection has to be empty because they simply have different numbers in them. AI is the set that includes I negative I. AJ has j negative j, and if I and j aren't equal, then those sets don't have any elements in common. So yeah, curly A is a partition of the integers. I'm not claiming that this is the only one, certainly. Maybe you came up with a completely different partition. I want to increase the difficulty here, and so question number 2, it's going to be the same as question number 1, but I'm going to ask if you can make the members of the partition infinite sets. Okay, so can you come up with an infinite partition of Z consisting of infinite sets? So that's a little bit harder. Like, what I would want is similar to what I have here, but instead of the individual members of the partition being finite, you'd want them to be infinite themselves. So I'm going to leave that question hanging and see if you can come up with that. All right, maybe a couple more questions then. Let's see, how about question number 3 is completely different, like, problem. Is the following collection of sets a partition of R? So what do you think about that? Yes or no? Pause. Okay, well, the answer is yes. And you can sort of walk through one by one. I think it's relatively clear. Each of these sets are non-empty. The union is all of R, because this set contains exactly those real numbers that this one doesn't. And these two sets have non-empty intersection because no number is both rational and irrational at the same time. All right, just one last exercise is this here. Q cross Q, the collection of ordered pairs of rational numbers. And this set, when put together, so this is one set, this is another set, is this a partition of R cross R? So just a discussion of what each of these sets are. This is the collection of ordered pairs of real numbers. This, as I mentioned, is the collection of ordered pairs of rational numbers. And then this is the collection of ordered pairs of irrational numbers. So decide on your answer. The answer is no. And I'll leave you to explain why. Okay, that is it.